In this video, we're going to look quickly at inverse functions. In order to know what an inverse function is, we have to know what a function is. So what is a function? Well, the definition of a function is a relation between an input and an output such that each input has only one output. It can certainly be the case, and if you think about x and y values, where x values are inputs and y values are outputs, just to kind of simplify the way we're talking about it, you can have multiple inputs that give you the same output. So multiple x values that give you the same y value, but you could only have one y value for each x value. And so that's kind of like a really, it's kind of abstract. So when you put an example to it, a better way, I think, or an additional way to describe a function is just the things that happen to the input. So for example, in this function here, the first thing that's happening to this x value is it's being multiplied by 3. Multiplied by 3. Okay? And then after that, we're adding 2. So this function is multiply by 3 and then add by 2. So we're taking our input, multiply by 3, added by 2, and then that gives us an output. Now, when we talk about functions on a coordinate plane, when we're talking in math, Cartesian functions, we have y as a function of x. So for all intents and purposes, y and f of x, these are interchangeable kind of symbols here for us. So y values are our outputs. Now, if we want to know what an inverse function is, we think about what the word inverse means. It means like reverse or invert, kind of turn something inside out. And so you could, what you need to do is do the opposite functions in the opposite operations, sorry, not functions, opposite operations in the reverse order. So instead of multiplying by 3 and adding 2, we're going to first take the input and subtract 2, and then we're going to divide by 3. Okay? Now, these operations, you can kind of think of them, they undo each other, sort of, right? So like, for example, we have multiplication and division. They kind of undo each other. They are inverse operations. We have addition and subtraction. Those are inverse operations. So let's look at what this would look like then if we took 3x, so we don't need to write that again, it's already there. Y equals 3x plus 2, right? That is our original function. Well, and now we want to take our input of x, we want to subtract 2, and then we want to divide that whole thing by 3. This is the inverse function of our previous one, and our notation for inverse functions is like this: f to the negative 1 of x is how you kind of is the notation for an inverse function. Let's look a little bit more closely at what that is really. So here's the two things we just said. Now notice the relationship between the inputs and the outputs here. If we take a negative 2 and plug it into our original f of x function, we'll get a negative 4 out. But if I take that negative 4 and plug it into my inverse function, I'll get the negative 2 out. You can see that these are going to be the same, and they will always be the same. So it's like our values that are part of our domain or our inputs, they get flipped. They now suddenly become part of our range, of our outputs. And conversely, for the inverse function, like the range of an inverse function is the domain of the original function, and the domain of the inverse function is the range of the original function. And so what that lets us do is kind of say, well, all right, if the x's are now y's and the y's are now x's, there's a whole new way that we can go about solving an inverse function. So some inverse functions are really pretty complicated. Like this one here, I don't actually know exactly how I would break down what is happening to the input and in which order. I think you would have to decompose this fraction a little bit and then kind of figure that out, which is troublesome. It's a difficult process. So instead, what we can say is, all right, this is another way to write this is as y is equal to x divided by x plus 2, right? Because f of x and y are the same. And then we're just going to switch our x and our x's and our y's, right? That's what we did. That's what inverse functions are doing. We're changing our x values and our y values around. So if we do that, we'll have this. Okay, I'm gonna write this in purple. We'll have x is equal to y divided by y plus 2. So all I've done here, and remember this was y up here, is I've changed wherever I saw an x, I've now written a y, and wherever I saw y, I've now written an x. And now we just have to solve this for y. Now this is not always necessarily super easy, but for this one we would do the multiplication property of addition. We'd multiply both sides by y plus 2, and we'd end up with xy plus 2x on the left side equals y on the right side. Let's get all the y's values by all the things with y in it on one side, so subtract xy from both sides. And we'll end up with, we'll end up with 2x is equal to y minus xy. And then we can factor a y out here on the right side. And then divide both sides by the 1 minus x. And so what this will give us then, our answer, our inverse function to the one we just had, is y is equal to 2x divided by 1 minus x. Now why on earth would we ever have to do this? Well, there are good reasons for doing this, and they typically come in the form of when we have to introduce an inverse function to like extract something. If we want to, it can be really helpful when relating inputs and outputs. Like say instead of an input, I've been given an output, and I want to know what the original input was. So I want to go backwards from a function. Like an inverse function undoes the original function. What does this mean, like graphically? Well, before we talk about that, let's look at one last example here. This is not at all the most complicated type of inverse function you'll come across. But if I just had this here, right, f of x is equal to x squared. Okay, so y is equal to x squared, and like we said, we're going to switch x and y and solve for y, so we're going to write x is equal to y squared. Now, how do you undo a squared? You undo a squared by taking a square root, right? And so what this tells us, and hopefully you know this, is that the absolute value of y is equal to the square root of x, right? So then y is equal to y is equal to plus or minus the square root of x. Okay, positive or negative the square root of x. Well, that is kind of strange. So to make this a little more clear, like maybe we should introduce a graph, okay? And what I've written here, if you know about inverse functions, you know what I've written here is actually incorrect. Even though we followed all the steps, there's something about this example and many others that illustrates something that we need to do with inverse functions. So here's Desmos, and what we have is just a blank graph. Now I'm going to show you the two graphs that we started with. So we started with a graph y equals, well, we had a function y equals 3x plus 2, and then our other function, our inverse function, was the quantity x minus 2 divided by 3. So those two functions are graphed right there. Okay, I'm going to turn those off for a second, and I want to go to, I want to show you the next one. Okay, so these two are the two that we did next. We had x divided by the quantity x plus 2, and then we had 2x divided by the quantity 1 minus x, and these were inverse functions of each other. There's a test you can do to make sure that you did it right when you're calculating an inverse function, and we'll talk about that really quickly, in a second. But those functions are there. And then now let's look at that last one. So the last one here was the x squared, right? Let me turn that other one off there. It's a little annoying to look at all of them. Okay, so here we have, this one's different. If you looked at the other ones, you saw that there was a lot of symmetry happening, but then this one has something different going on. The reason that this one is different is because y equals x squared is not a specific kind of function called a one-to-one function. What a one-to-one function is first of all, it meets the first criteria of being just a normal function, that every input has just one output. But it would additionally need to have, in order to be a one-to-one function, the property that every output has just a single input. Now, you may have heard of the vertical line test. Okay, the vertical line test is just when you drag a vertical line across the graph of a function, and as long as it only intersects that graph once, then it's a function, right? Well, similarly, there's something called a horizontal line test. Now, a horizontal line test tests for the other thing. Is there a single output? Is there only a single input for every output? Well, here are y values, right? Nope. All throughout the range of this original function. In fact, all throughout the domain, really, we have the situation where we have 2 points of intersection. So y equals x squared is not an inverse function, which means then that and if we, the other thing we wrote on the other thing that we wrote on our previous thing we were looking at was that we had negative the square root of x too, right? We had square root of x and we had negative square root of x. So basically we have these items, right? Now this does not pass the vertical line test even, because if I put the vertical line test back on, it intersects twice. So the inverse function of our x squared is not a function. So you can't have an inverse function that isn't a function. And so what does that mean about y equals x squared? Does it have an inverse? The answer is no. But y equals x squared does not have an inverse function because y equals x squared is not a one-to-one function. However, that doesn't mean we can't use the idea of an inverse function with y equals x squared. What we need to do is restrict the domain of y equals x squared. So what that would look like then, and this is a Desmos shorthand here, but if this is learning, if you've not done this before, but I want anywhere from x from 0 to infinity. I don't know how you can do infinity. Basically, x can be greater than or equal to 0, right? So x can be greater than or equal to 0. Now we've just restricted the domain of x squared to be only positive values and 0. Well, now that function y equals x squared with that domain restriction, that is a one-to-one function. It passes both the horizontal and vertical line test. Okay, it only ever crosses once, and that would rule out this negative part of our inverse function to be only positive square root of x. So that's kind of the takeaway here, is that we need to restrict the domain of non-one-to-one functions in order to come up with what the inverse function is correctly. Now, something that is very important also to know about inverse functions is that they are reflections of themselves, or they are symmetrical about the line y equals x. So here I have the line y equals x, and I'll just zoom in a little bit on this so you can see how there's symmetry about that line. I'll turn off those horizontal and vertical lines. And then I'll show you also that, this applies to any inverse function. So not just that one, but the other one we did, right? Those lines, they intersect on the line y equals x, and they're reflections of each other about that line. Same deal with this more complicated looking one. Sorry, I turned the other one off. So you can see how they reflect about the line y equals x. Okay, so last thing, I said that I would show you, how do you know that you have inverses of how do you know that the functions are inverses of each other if you just see them? Well, let's look at these two as an example here, and we'll just quickly we'll quickly move our two functions right next to each other. So we had 3x plus 2 and x minus 2 equals 3. If we called, we know actually, right, that this was f of x, that this was f of x, and that our other one was f inverse of x, or inverse function, then if f of f inverse of x is equal to 0, is not equal to 0, is equal to x, and if f inverse of x, f inverse of f of x is equal to x, then we have inverse functions. These are called compound functions. We say it's like f of g of x, g of f of x. You've probably seen those before. So all we're going to do is plug f inverse of x into x in the f of x, which means 3 times, now we're going to plug, so this is the first one. We're going to plug f inverse of x in here. We have x minus 2 divided by 3. and then we had a plus 2 afterwards. So this would be, we cancel those 3's out, we'd have x minus 2 plus 2, this equals x, it checks out. Okay, it will work the other way, take my word for it. Okay, and that's how we can confirm just algebraically that functions are inverses of each other. So, last thing to note, just kind of summarize what we talked about. The domain of a function is the range of its inverse, and the range of a function is the domain of its inverse. Inverse of a function is a reflection across the line y equals x. So the inverse function is a reflection of the original function across the line y equals x. And if we don't have a one-to-one function to begin with, then we need to state a domain restriction to our original function in order to have a inverse function. That part is really important because if we didn't have that, you can imagine the whole point of a function is that it's reliable. We want to plug in a number and know what's going to come out. It's predictable, right? We can't have a function if we plug something in and we're not sure what's going to come out. So if we had an inverse function of a non-one-to-one function, we wouldn't meet that criteria, right? We could plug something into an inverse function and get a number of different things out, which that's not good. So that's the whole reason why we need these domain restrictions.